Hello, and thank you for joining. My name is Derek Kane, and today we're going to get into the topic of hidden Markov models. This lecture is just one lecture in a series of lectures diving into topics of data science, predictive analytics, and machine learning. If you're interested in those topics, please feel free to check out the other videos and subscribe to the channel. Okay, let's begin. The overview of topics that we're going to get into today are going to first start off with an introduction to Markov processes and Markov models. What are they, how do they work, and how can we work with them? Once we have an understanding of a Markov process, then we'll dive into the concept of a hidden Markov model. After we have this established from a conceptual framework, we're going to dive into the statistics of the algorithms a little bit. Most notably, we'll start with the forward algorithm. Then after we've tackled the forward algorithm, we'll get into the Viterbi algorithm. Then finally, the Baum-Welch algorithm. Once we have all of these algorithms firmly understood, then we'll move into a practical example where we're going to apply the Viterbi and the Baum-Welch algorithm in an example to help predict the price of a stock. Often, we are interested in finding patterns which appear over a space of time. Most of the predictive examples we've talked about really are looking at time as a fixed component, and we're not even concerning ourselves with the sequence of events. Okay, but when we're working with real-world data, the development over time is of importance for us. These types of patterns, they're observed in many areas in nature. For example, the pattern of commands someone uses in instructing a computer. So as I'm typing a computer, what are the letters that I'm typing and what's the order in which I'm typing them? Sequences of words and sentences. So for the types of words that are being used, nouns, verbs, adjectives, so on and so forth, and the sequence of these words in sentence structures. Continuing on that path, there are additional applications in natural language processing technologies. So the sequence of phonemes in spoken words. How are we inflecting our tone for particular words and using them to communicate our language. And there are some fun ways, such as popcorn popping in an air popper. The order in which the kernels are exploding. These are all processes that can be understood through a Markov process. But really, what we are most interested towards understanding with a sequence of events processes is whether or not this sequence produces useful patterns which can be modeled. Let's first consider a set of traffic lights. Now, when I look at a traffic light, the sequence of lights is red, red amber if you're in Europe, green, amber, red. This sequence can be pictured as a state machine, okay, and we refer to this as a trellis diagram, with different states of the traffic lights follow each other. So for example, if I'm sitting at an intersection and I have a red stoplight, prior to it turning green, and this is primarily in Europe, I know my American colleagues, we definitely don't see this, but you see it both show red and yellow, which means be prepared to go. Then it turns green, and we're driving through our intersection, and then after it's been green for a while, it turns back to yellow, and after it's yellow, then the sequence returns. Now notice that each state is dependent solely on the previous state. So if the lights are green, an amber light will always follow. That is, this system is deterministic. And this deterministic system are relatively easy to understand and analyze once the transitions are fully known. The system is referred to as an observable Markov process. Now let's consider the simple example of someone trying to deduce the weather from a piece of seaweed. Folklore tells us that soggy seaweed means wet weather, while dry seaweed means sun. If the seaweed is in an intermediate state, damp, well, then we can't be sure. However, the state of the weather is not restricted to the state of the seaweed, so we may say on the basis of an examination that the weather is probably raining or sunny. A second useful clue would be the state of the weather on the preceding day, or at least its probable state. By combining knowledge about what happened yesterday with the observed seaweed state, we might come to a better forecast for today. This is typical of the type of system we will consider in this tutorial. First, we will introduce systems which generate probabilistic patterns in time, such as the weather fluctuating between sunny and rainy. We then will look at systems where what we wish to predict is not what we observe. The underlying system is hidden, and we'll get into this in the next couple of slides. In our previous example, the observed sequence would be the seaweed, and the hidden system would be the actual weather. We then will look at some problems that can be solved once the system has been modeled. For the example, we might want to know what the weather was for a week given each day's seaweed observation. Given a sequence of seaweed observations, is it winter or summertime? Intuitively, if the seaweed has been dry for a while, it might be summer, and if it's been soggy for a while, well, it might be winter. Well, how would our weather example look like as a Markov process? So let's build some trellis diagrams based off of the observable weather, just to kind of ease us into these topics. Now imagine we have three states of weather. We have sunny, cloudy, and rainy. Each state depends only upon the previous state. Here is a possible sequence, with each sequence taking a single day. So each observation is of 1 day apart. So we might have 1 day where it is sunny. The next day could be cloudy. And then the following day might be rainy. Now, there is another possible sequence. One sunny day could then lead to another sunny day. And when this happens, this loop is often referred to as a self-transition. So I can have a sunny day today, and tomorrow might also be sunny. Okay, so these are all different possibilities that we have when looking at our Markov process. We can continue to build all of the observable possibilities until we reach the following diagram. So I have my sunny, my cloudy, and my rainy days. Well, from a sunny standpoint, it can be one of these three states, and we see this as indicated by the diagram. Now, if I have a cloudy day, it can be one of the three states as indicated by the pattern that we're showing. And then finally, on a rainy day, we can see the observations essentially close the loop, and we now have a self-contained system where all of the possibilities have been modeled. We can also construct the probabilities for these various weather patterns based upon observations. So what is the probability of the next day being sunny after a day is sunny? In this case, we see it as a 0.50. So if you look on the left-hand side, we have a probability of 0.50 written out. And I tried to color code these to make it a little easier in the next couple of slides when we start working with these figures a little bit. But we can, through this approach, say, okay, well, what's the probability of it being sunny when the preceding day was sunny as well? And what's important to note is that the total sum of each of these colored probabilities is equal to 1. This system of observed probabilities can be represented in a matrix format. This matrix is also referred to as a transition matrix. So we can take our Markov process, which we had just modeled, and we see on the right-hand side, and I can just represent that in a matrix. And we see on the left-hand side, we have our weather of yesterday versus our weather patterns that we see today. And we see the corresponding values put in the matrix in the correct locations. In some cases, the patterns that we wish to find are not described sufficiently by a Markov process. If we return to our weather example, a hermit may perhaps not have access to direct weather observations, but he does have a piece of seaweed. Remember, folklore tells us that the state of a seaweed is probabilistically related to the state of the weather. The weather and seaweed states are closely linked. In this case, we have two sets of states. We have the observable states, which are the states of the seaweed, whether they're soggy or dry, and we have our hidden states, which is the state of the weather. We don't actually have the observations for this Markov process. And what we wish to do is we want to devise an algorithm for the hermit to forecast the weather from the seaweed and the Markov assumption without actually ever seeing the weather. Well, let's dive into this topic a little more. In such cases, the observed sequence of states is probabilistically related to the hidden process. We model such processes using a hidden Markov model where there is an underlying hidden Markov process changing over time and a set of observable states which are related somehow to the hidden states. It is important to note that the number of states in the hidden process and the number of observable states may be different. So you can have 3 observable states that are related to 4 hidden states. In a 3-state weather system, so sunny, cloudy, and rainy, it may be possible to observe 4 grades of seaweed dampness: dry, dryish, damp, and soggy. And we'll talk about this a little more. So looking at our model from earlier, our Markov process, which is the weather patterns that we were talking about, in this case it's a set of hidden states. Well, we have our observable states residing on the top. So we know what the seaweed is actually showing us. We can tell whether or not it's soggy, it's damp, dryish, and dry. And what we're trying to do is we're trying to create the connection from a piece of soggy seaweed to the various weather states. And we can see from each one of these states that they're connected to the hidden Markov process in some manner. And that's what we mean by a hidden Markov process. The diagram shows the hidden and observable states in the weather example. It is assumed that the hidden states, the true weather, are modeled by a simple first-order Markov process. And so they are all connected to each other. And there are other types of Markov processes for simplicity's sake and for the purpose of this tutorial. Everything that we're going to be looking at is going to be a first-order Markov process. The connections between the hidden states and the observable states represent the probability of generating a particular observed state, given that the Markov process is in a particular hidden state. It should be clear that all probabilities entering an observable state will sum to 1, since in the above case it would be the sum of the probability of an observation of the sun, probability of an observation of cloud, and a probability observation of rain. In addition to the probabilities defining the Markov process, we therefore have another matrix, termed the confusion matrix or emission matrix, which contains the probabilities of the observable states given a particular hidden state. For the weather example, the emission matrix is shown on the left. Notice that the sum of each matrix row is equal to 1. Each probability in the state transition matrix and in the emission matrix is time independent, That is, the matrices do not change structure in time as the system evolves. In practice, this is one of the most unrealistic assumptions of Markov models about real processes. And this is something that is very important for us to understand. So, as systems move over time, the nature of the relationships of the patterns can be fluid and dynamic. The matrix structure can evolve. It can compact and it can expand depending on real observations and how the system actually works. But in our case, the structures are going to remain fixed and constant. Okay, and that is something when working with hidden Markov models that we have to understand and pay very close attention to. Once a system can be described as a hidden Markov model, 3 types of problems can actually be solved: evaluation, decoding, and learning. And we'll talk about these in detail. The first 2 are pattern recognition problems. So finding the probability of an observed sequence given a hidden Markov model, which is the evaluation. The second one is finding the sequence of hidden states that most probably generated an observed sequence, so a decoding type of problem. The third problem is generating a hidden Markov model given a sequence of observations, and a learning type of problem. And we'll talk about all 3 of these a little more. First, let's dive into evaluation. Consider the problem where we have a number of hidden Markov models describing different systems and a sequence of observations. We may want to know which hidden Markov model most probably generated the given sequence. For example, we may have a summer model and a winter model for the seaweed. Since behavior is likely to be different from season to season, we may then hope to determine that the season on the basis of a sequence of dampness observations. We will use the forward algorithm to calculate the probability of an observation sequence given a particular hidden Markov model, and hence choose the most probable hidden Markov model. And there are other types of approaches beyond the forward. For the purpose of this presentation, that will be our primary focus. Decoding. Finding the most probable sequence of hidden states given some observations. The question usually of most interest with hidden Markov models is to find the hidden states that generated the observed output. In many cases, we are interested in the hidden states of the model since they represent something of value that is not directly observable. Consider the example of the seaweed and the weather. A blind hermit can only sense the seaweed state, but needs to know the weather. We use the Viterbi algorithm to determine the most probable sequence of hidden states given a sequence of observations and a hidden Markov model. And finally, learning. Learning involves generating a hidden Markov model from a sequence of observations. The hardest problem associated with hidden Markov models is to take a sequence of observations from a known set, known to represent a set of hidden states, and fit the most probable hidden Markov model. We can use the Baum-Welch expectation maximization algorithm to identify the local optimal parameters for the hidden Markov model. Now that we've talked about these 3 types of problems that can be solved with hidden Markov models, we're going to dive into each one of them in detail over the next portion of the presentation. And the first one we're going to start off with is the forward algorithm. There are a number of ways to find the probability of an observed sequence. We want to find the probability of an observed sequence given a hidden Markov model where the parameters are known. And this is important, the parameters have to be known. Consider the weather example. We have a hidden Markov model describing the weather and its relation to the state of the seaweed, and we also have a sequence of seaweed observations. Suppose the observations for 3 consecutive days are dry seaweed, damp seaweed, and soggy seaweed. On each of these days, the weather may have been sunny, cloudy, or rainy. We can picture the observations and the possible hidden states as a trellis, and we have a trellis diagram on the left-hand side which shows these different states and all the possibilities. Each column in the trellis shows the possible state of the weather, and each state in one column is connected to each state in the adjacent columns. Each of these state transitions has a probability provided by the state transition matrix. Under each column is the observation at that time. The probability of this observation given any one of the above states is provided by the emission matrix. It can be seen that one method of calculating the probability of the observed sequence would be to find each possible sequence of the hidden states and sum these probabilities. For example, there would be 3 raised to the third equaling 27 possible different weather sequences, and so the probability is described as follows. And I'm not going to read the entire formula, but we can walk through the entire flow of this trellis diagram and determine the maximum number of probabilities. Calculating the probability in this manner is computationally expensive, particularly with large models, and we can find that we can use the time invariance of the probabilities to reduce the complexity of the problem. So computational efficiency when working with this machine learning algorithm and this technique is going to be very important. And so the algorithms that we're going to dive into help to resolve some of these issues in a very elegant way. Now let's take a look at the reduction of complexity using recursion and recursive techniques. We will consider calculating the probability of observing a sequence recursively given a hidden Markov model. So on our trellis diagram on the right, we now see above where we have t equals 1, t equals 2, t equals 3, and those are just 3 independent dates. We will first define a partial probability, which is the probability of reaching an intermediate state in the trellis. We then show how these partial probabilities are calculated at times t equals 1 and then t equals n greater than 1. Suppose throughout that the t-longed observed sequence is as follows. Okay, so the y in this case represents the observed sequence that we have. Now let's consider the trellis showing the states in first order transitions for the observation sequence dry, damp, and soggy. We can calculate the probability of reaching an intermediate state in the trellis as the sum of all possible paths to that state. For example, the probability of it being cloudy at t equals 2 is calculated from the paths. We denote the partial probability of state j at a time t as j. This partial probability is calculated as j is equal to the probability of the observation of the hidden state is j times the probability of all paths to state j at time t. The partial probabilities for the final observation hold the probability of reaching those states going through all possible paths. The final partial probabilities are calculated from the following paths of our seaweed trellis diagram. It follows that the sum of these final partial probabilities is the sum of all possible paths throughout the trellis, and hence is the probability of observing the sequence given the hidden Markov model. We calculate partial probabilities as in the special case where t is equal to 1, there are no paths to the state. The probability of being in a state at t equals 1 is therefore the initial probability, i.e. the probability of the state where t equals 1 is equal to the probability of the state. And we therefore calculate partial probabilities at t equals 1 as this probability multiplied by the associated observation probability. Thus, the probability of being in state J at initialization is dependent on that state's probability together with the probability of observing what we see at that time. And we'll get into these initial state ideas and some of the statistics a little more later. I just want to introduce the concepts. So calculating alphas at time of t being greater than 1, let's look at this scenario. We recall that a partial probability is calculated as J is the probability of the observation where the hidden state is J times the probability of all paths to state J at time of t. We can assume recursively that the first term of the product is available, and now consider the term probability all paths to state J at time of t. To calculate the probability of getting to a state through all paths, we can calculate the probability of each path to that state and then sum them. The number of paths needed to calculate alpha increases exponentially as the length of the observation sequence increases, but the alphas at the time t-1 give the probability of reaching that state through all previous paths. So we can define alphas at time t in terms of those at time t-1 through the following expression. Therefore, we calculate the probabilities as the product of the appropriate observation probability. That is, the state J provoked what is actually seen at time t plus 1, with the sum of probabilities of reaching that state at that time. This latter comes from the transition probabilities together with alpha from the preceding stage. Notice that we have an expression to calculate alpha at time t plus 1 using only partial probabilities at time t. We can now calculate the probability of an observation sequence given a hidden Markov model recursively. For example, we use alphas at t equals 1 to calculate alphas at t equals 2, alphas at t 2 to calculate alphas at t equals 3, and so on until t reaches the full amount of time, capital T. The probability of the sequence given the hidden Markov model is then the sum of these partial probabilities at time t equals t. And we had talked about this before. We can compare the computational complexity of calculating the probability of an observation sequence by exhaustive evaluation and by the recursive forward algorithm. We have a sequence of t observations O. We also have a hidden Markov model with n hidden states. So we're going to dive into a practical example here. Okay. An exhaustive evaluation would involve computing for all possible execution sequences. So the x in this case is representing the hidden state. And then through the formula, we can calculate the sum of the probability of observing what we do. Note that the load here is exponential in t. Conversely, using the forward algorithm, we can exploit knowledge of the previous time step to compute information about the new one. Accordingly, the load will only be linear in t. So to summarize, and I know I've thrown a lot of statistics at us in a short period of time, is our aim is really to find the probability of a sequence of observations given a hidden Markov model. We reduce the complexity of calculating this probability by first calculating partial probabilities, the alphas. These represent the probability of getting to a particular state S at time of t. We then see that at time t equals 1, the partial probabilities are calculated using the initial probabilities from the p-vector and the probability of the observation against the probability of the state from our confusion matrix. Also, the partial probabilities at time t greater than 1 can be calculated using the partial probabilities at time t equals 1. This definition of the problem is recursive, and the probability of the observation sequence is found by calculating the partial probabilities at time t equals 1, 2, so on and so forth, and then adding all of the alphas at t equals t. Notice that computing the probability in this way is far less expensive than calculating all the probabilities for all of the sequences and then adding them. Now that we've gone through this, let's just go ahead and formally define the forward algorithm. We use the forward algorithm to calculate the probability of a t-long observation sequence. Okay, so this is our observed sequence here, where each of the y is one of the observable set. Intermediate probabilities, the alphas, are calculated recursively by first calculating alpha for all states at t equals 1. Then, for each time step, t equals 2, t equals 3, so on and so forth, the partial probability is calculated for each state. The product of the appropriate observation probability and the sum over all possible routes to that state, exploiting recursion by knowing these values already for the previous time step. Finally, the sum of all partial probabilities gives the probability of the observation given the hidden Markov model. To recap, each partial probability at time t greater than 2 is calculated from all the previous states. Using our weather example, the diagram shows the calculation for alpha at t equals 2 for the cloudy state. This is the product of the appropriate observation probability b and the sum of the previous partial probabilities multiplied by the transition probabilities of alpha. So finally, we can visually represent this as we have to establish some initial state probabilities. What are the probabilities of sunny, cloudy, and rainy? And what are our observable states versus our hidden states? Once we do this, we can then create our confusion matrix and our state transition matrix. So in summary, we use the forward algorithm to find the probability of an observed sequence given a hidden Markov model. It exploits recursion in the calculations to avoid the necessity for exhaustive calculation of all paths through the execution trellis. Given this algorithm, it is straightforward to determine which of a number of hidden Markov models best describes a given observation sequence. The forward algorithm is evaluated for each, and that giving the highest probability is selected. Well, that concludes our section on the forward algorithm. Now we're going to dive into the Viterbi algorithm. Since we have a solid understanding of how the forward algorithm works in evaluation techniques, let's shift focus and review a decoding hidden Markov model scenario with the Viterbi algorithm. And on the right-hand side, we have a picture of the inventor, Andrew Viterbi himself. In practice, we often wish to take a particular hidden Markov model and determine from an observation sequence the most likely sequence of underlying hidden states that might have generated it. The Viterbi algorithm is designed to help solve this form of the problem. And in our practical example we will see exactly how this works with real data. As with our example with the forward algorithm, we're going to dive into the statistics in a very similar way with the Viterbi. Okay. So we can use a picture of the execution trellis to visualize the relationship between the states and the observations. We can find the most probable sequence of hidden states by listing all possible sequences of hidden states and finding the probability of the observed sequence for each of the combinations. The most probable sequence of hidden states is that combination that maximizes the probability of the observed sequence from the hidden state combinations. As with the forward algorithm, we can use the time invariance of the probabilities to reduce the complexity of the calculation. We will consider recursively finding the most probable sequence of hidden states given an observation sequence in a hidden Markov model. We will first define the partial probability, delta, which is the probability of reaching a particular intermediate state in the trellis. We then show how these partial probabilities are calculated at t equals 1 and at t equals n greater than 1. These partial probabilities differ from those calculated in the forward algorithm, since they represent the probability of the most probable path to a state at time t and not a total. Okay, and that's a key difference when working with these algorithms. Let's consider the trellis from a couple slides ago, showing the states and the first order transitions for the observation sequence, dry, damp, or soggy. For each intermediate and terminating state in the trellis, there is a most probable path to that state. So, for example, each of the three states at t equals 3 will have a most probable path to it, perhaps something like this. And we see on the right-hand side what these most probable paths would look like. We will call these paths partial best paths. Each of these partial best paths has an associated probability, the partial probability, or delta in this case. Unlike the partial probabilities in the forward algorithm, delta is the probability of one most probable path to the state. Thus, delta is the maximum probability of all sequences ending at state I at time t, and the partial best path is the sequence which achieves this maximal probability. Such a probability and partial path exists for each possible value of I and t. In particular, each state at time t equals t will have a partial probability and a partial best path. We find the overall best path by choosing the state with the maximum partial probability and choosing its partial best path. So when we're calculating deltas at time of t equals 1, we then calculate the delta partial probabilities as the most probable route to our current position, given particular knowledge such as observation probabilities of the previous state. When t equals 1, the most probable path to a state does not sensibly exist. However, we use the probability of being in that state given t equals 1 and the observable state of k equals 1. As in the forward algorithm, this quantity is compounded by the appropriate observation probability. So now let's look at a scenario where we're calculating deltas at a time of t is greater than 1. We now show that the partial probabilities delta at time t can be calculated in terms of the deltas at time t minus 1. Let's consider the trellis to the right-hand side. We consider calculating the most probable path to the state x at time t. This path to x will have to pass through one of the states A, B, or C at time of t minus 1. Therefore, the most probable path to x will be one of some sequences of states to A, then to x, a sequence of states B, then to x, some sequence of states C, then to x. We want to find the path ending AX, BX, or CX, which has the maximum probability. Now, if we recall that the Markov assumption says that the probability of a state occurring given a previous state sequence depends only on the previous n states. In particular, with a first-order Markov assumption, the probability of x occurring after a sequence depends only on the previous state. So for example, it's the probability of the most probable path to A is equal to the probability of x to A times the probability of the observation to x. Following this, the most probable path ending AX will be the most probable path to A followed by x. Similarly, the probability of this path will be the probability of the most probable path to A is equal to probability of x to A times the probability of observation to x. So the probability of the most probable path to x is represented as follows. Okay, it's the max of A, B, and C, the paths, which is the probability of I at time t minus 1, times the probability of x to I, times the probability of the observations at time of t to x, where the first term is given by delta at t minus 1, the second by the transition probabilities, and the third by the observation probabilities. Here's a generalization of that previous formula that we were looking at with the probability of the partial best path to a state I at a time t when the observation kt is seen as follows. Here we are assuming knowledge of the previous state using the transition probabilities and multiplying by the appropriate observation probability. We then select the maximum probability. So let's consider the trellis to the right-hand side. At each intermediate and end state, we know the partial probability of delta of I of t. However, the aim is to find the most probable sequence of states through the trellis given an observation sequence. Therefore, we need some way of remembering the partial best paths through the trellis. Okay, and this is a critical point. Recall that to calculate the partial probability delta at time t, we only need the deltas for time t minus 1. Having calculated this partial probability, it is thus possible to record which preceding state was the one to generate delta I of t. That is, in what state the system must have been at time t minus 1 if it is to arrive optimally at state I at time of t. This recording or remembering of this information is done by holding for each state a back pointer, okay, in this case it's phi, which points to the predecessor that optimally provokes the current state. Formally, we can write this as follows. Here the argmax operator selects the index j, which maximizes the bracketed expression. Let's take a look at this formula again. Okay, so let's just kind of keep it front and center now. Notice that this expression is calculated from the deltas of the preceding time step and the transition probabilities and does not include the observation probability, unlike the calculation of the deltas themselves. This is because we want these phi's to answer the following question. If I am here, by what route is it most likely that I arrived? This question relates to the hidden states, and therefore confusing factors due to the observations can be overlooked. Well, there are some advantages to this approach, and we should talk about them. Using the Viterbi algorithm to decode an observation sequence carries two important advantages. There is a reduction in computational complexity by using the recursion. This argument is exactly what we use to justify our use of the forward algorithm. Okay. But the second one, I think, is more important to look at. The Viterbi algorithm has the very useful property of providing the best interpretation given the entire context of the observations. And an alternative to it might be, for example, to decide on the execution sequence. So let's consider the following in this case. So X is our hidden state, where we've talked about where we have the following assumptions held. In this case, decisions are taken about a likely interpretation in a left to right hand manner, okay, with an interpretation being guessed given an interpretation of the preceding stage. Okay, so it's moving in sequence from left to right. This approach, in the event of a noise garble halfway through the sequence, will wander away from the correct answer. Conversely, the Viterbi algorithm will look at the whole sequence before deciding on the most likely final state, and then backtracking through the 5 pointers to decide how it will have arisen. This is very useful in reading through isolated noise garbles, which are very common in live data. So I just want to take a moment just to focus on this slide, okay, rather than just rushing through it. So in data that we're working with, very often that we're going to have spikes and nuances to the data. Okay, and when we have these spikes, we want to make sure that they're encompassed in the algorithm itself, and it's weighing the entire effect of all the data points when creating the final algorithm. Okay, and that's what the Viterbi algorithm focuses on, is it actually looks at the entire sequence before deciding on the most likely final state. Okay, so this is one of its greatest strengths and is a very important consideration when working with hidden Markov models. Here is an example going through our weather example, like we had done previously with the forward algorithm, that shows the calculation for individual deltas and phi and for the cloudy state. The calculation of deltas is similar to the calculation of the partial probability, the alphas, in the forward algorithm. So bringing all of this together, when working with the Viterbi algorithm, we have our observable states and our hidden states, and our initial state probabilities. We can feed it through the algorithm, and it will create our confusion matrix and our state transition matrix. Well, now we've talked about the forward algorithm and the Viterbi algorithm, I want to touch upon the Baum-Welch EM algorithm. The useful problems associated with hidden Markov models are those of evaluation and decoding, the forward and the Viterbi. They permit either a measurement of a model's relative applicability or an estimate of what the underlying model is doing, so what really happened. It can be seen that they both depend upon foreknowledge of the hidden Markov model parameters, the state transition matrix, the observation matrix, and the p vector. There are, however, many circumstances in practical problems where these are not directly measurable, and they have to be estimated, which is essentially a learning problem. Okay, so as we move forward talking about this, I just want to quickly show that we have Lloyd Welch on the right-hand side. I couldn't find a picture of Baum to include, so all we have is Welch. And this is really what the Baum-Welch algorithm is designed to resolve, is this learning problem. Imagine that we have a data set of observations, and we want the parameters of the hidden Markov model that generated this data. How do we leverage a hidden Markov model for prediction when we do not have an understanding of the relationships between the observed and hidden states? The problem is that there is no known way to analytically solve for the model which maximizes the probability of the observation sequence. The calculation space is too large for an exact calculation. So in this case, we run into fundamental limitations in our machine learning techniques because the space is just too large to actually calculate. This issue can be circumvented through the use of heuristic methods. While a heuristic methodology only creates a partial solution, the results are extremely useful. Okay. The result of this work is the creation of locally optimal parameters. Okay, so even though we can't compute the entire space, there is still some value to the work, and we'll see when we get into our practical example. Now, one important thing to note is that the Baum-Welch EM algorithm is more complex in nature than the forward algorithm and the Viterbi algorithm. And for this reason, it will not be presented here in full. So I'm not going to go into the same type of statistical derivation of the formulas here, but more just understanding how the Baum-Welch EM algorithm works in practice. Okay, if you're interested in this, there are lots of resources that you can find that dive into this topic deeper. So I'm working with a hidden Markov model, and the transmission, the emission, and initial distribution probabilities, they're all unknown. Well, when we're working with this, I first need to set some parameters and some probabilities to some initial values. Okay. And these values can be taken from the following. It can be some form of a uniform distribution. I can incorporate some prior knowledge, or I can take a purely random value, but it just can't be flat across the parameters. Then we need to figure out the probability of a hidden state transition. So we postulate that the transition at every single spot in every single observed sequence separately. Then we see how the probabilities compare to the best probabilities for those observed sequences. Then we use this ratio to update the transition probability. We then follow a similar procedure for the emission symbol from the hidden state. The next step calculates the probabilities of the learning set, and then we rinse and repeat, and we do this over and over through a recursive fashion. Successive iterations increase the probability of the data, and we stop the procedure when the probability stops increasing significantly and converges. Okay, and it's usually measured as a log likelihood ratio. So rather than talking about it in a statistical sense, let's think about it in a more practical way. Okay. Let's go back to our seaweed weatherman example. For discussion purposes, we're going to simplify the scenario to only wet or dry seaweed for our observed state. Okay, I know we had talked about damp and soggy earlier, but we're only going to just focus on two now. Our seaweed weatherman, our hermit, while walking on the shores, finds either wet or dry seaweed. I also know that either sunny or rainy weather can be predicted from the seaweed. And this implies that there are only two hidden states, sunny or rainy. So I'm also removing the cloudy from our example. Okay. And we're just keeping it simple just so we can reinforce what the technique is actually doing. With the two hidden states, I needed to invent a transition matrix and an emission matrix. Okay, so here an example of these two matrices. We also need to decide on the initial weather forecast probabilities. So what do I think, the probability of the weather being sunny is going to be, or the probability of it being rainy? Now I'm going to use my own personal experience. I'm going to say that a chance of it being sunny is going to be a probability of 0.3, and the probability of rainy will be 0.7. So let's imagine we have the following set of 9 observations. Okay. So I have my previous day and my current day's observation where I see wet seaweed and wet seaweed. Then I have another day where I see wet seaweed, and then I have a day where I see wet seaweed, dry seaweed. And I have a day of dry seaweed, dry, wet, and so on and so forth. I can use these two matrices in these initial configurations, and I can actually calculate what these probabilities are. So for an example, if I have a wet observation coming from a sunny to rainy sequence, we would actually calculate the probability as follows. So take 0.3 times 0.2 times 0.5 times 0.9, which equals 0.027. From this, we can estimate our transition matrix. So I can take these probabilities of all these different sequences going from sunny to rainy, and then I can look at the best probability of the sequence. So our estimate for the sunny to rainy transition probability is now 0.285, which is the summation of the total, divided by 2.4474, which is the summation of the best sequence, which gives me 0.116. So then I'd go through this entire process and I'd calculate the rainy to sunny transition, the rainy to rainy transition, the sunny to sunny transition, and then I take these results and I normalize them so that they add up to 1, and then I update my transition matrix. Now we will estimate our new emission matrix. The initial probabilities can also be updated through the following approach. So I assume all sequences start with the hidden state sunny, and I calculate the best probability. Then I assume all sequences start with the hidden state rainy, and I calculate the best probability. And then finally, I normalize to 1. This method has now created an updated transition, emission, and initial probabilities. We will repeat this method until the probabilities converge, at which point the algorithm completes the run. Now, one important thing to note, if we guess the wrong number of hidden states, it will be clear when we run this model, though it is a bad strategy to go through a huge range of possible hidden states to find the best model. So, rather than just randomly choosing our hidden states, we should ground it in some type of empirical research. But if running the Baum-Welch algorithm, we will find if our hidden states don't make intuitive sense. And when we do this, that essentially leads to over-optimization type problems or overfitting problems. Okay, well, now we've gone through the major components of hidden Markov models. Let's dive into a practical example, and this example will show how we can use hidden Markov models in practice in a business context. The first thing that I like to do before diving into any models is I first need to understand the data. There are many applications for utilizing hidden Markov models. The stock market is an example where we can draw from our knowledge of hidden Markov models to model how the system behaves. The data set that we're going to be using, we will scrape off of the World Wide Web, and we'll grab this from Yahoo using the quantmod library in R, and this data set contains information related to a particular stock's performance. The goal for this exercise will be to decode the hidden Markov model using the Viterbi algorithm, and then utilize the Baum-Welch EM algorithm to make a prediction for the next day's value of the stock price. So first, I always like to gain a sense of the information that I'm working with. Now, you can go through an extensive exploratory data analysis process, but for now, I just want to understand the shape of this data from the time series. So we're going to extract information related to the stock TWII, and then we'll use the plot function in quantmod to review the stock data. The data set contains information related to the opening and close stock price for a given day, the high and low price, and the stock value. Sometimes I like to look at this data in a raw table format. So this is what I would see if I was to open up this table in Excel. Okay, and that just gives you a sense for the type of information that's contained and how we can work with it. Now, what we are interested in modeling with our hidden Markov model is the difference between the close value and the opening value for the current day. So how does the system change for a particular day? Okay, so it's the difference between the close and the open value for a given day. So now I'm going to walk into a little more of our code here. Most of my tutorials don't get into the our code as much, but I feel with hidden Markov models, this would be a good one to incorporate a little. So we're going to pull in our financial data from Yahoo. So I'm going to invoke in R the quantmod library, and I'm just going to type my stock symbol and where I'm going to get it from, and the time frame I want to pull the data in. Okay. Then I'm going to chart my series, which was the chart that we had looked at previously. And then we're going to work with the data and we're going to subset it. And we're going to create some training data from it as well. Now notice that I subset the data from 1/1/2013 to present day. I just type in this case, a 12/31/2015. because that's just takes us to the end of the year, and I just want to make sure that I have a good set of data that I'm working from that's current. Also, we will calculate the difference between the open and closed values and store this data set off for our model building. So we talked about using our difference between the closed and open values. Well, using the cbind function, we can actually create this and store this off. The next step will involve fitting our hidden Markov model through the RHMM 2.0.3 package. Now, this is a package that has been depreciated from CRAN. Okay, so you might have to either install an archived older version or go to RForge and get the most current one. But in this case, I'm using the 2.0.3 package. For this example, we are identifying 5 hidden states to the models with a series of different 4 distributions for each hidden state. Okay, so this is a little more complex than what we were working with before. We have different distributions for each of these states that we're working with now. Okay, but if you see my commented section of the HM model down below, this is how we would just have a simple 5-state hidden Markov model. And additionally, we are specifying a number of iterations for the algorithm to process to equal 2000. And this is to ensure convergence. Okay, so different models, packages in R, might have different control mechanisms. I want to ensure that I have convergence, so I don't know how many times this algorithm is going to be running. So I specified it to be 2000 in this case because I'm sure that after running this iterative process 2000 times, I'm going to have convergence. Okay. So when you're working with this in practice, just make sure that you're considering how many iterations that you're running and the performance. Okay. Once we're done with this, we're going to print the model, and I'm going to show you what the print looks like in the next screen. Well, here is the output of the model. Okay, so we see that we have 5 states hidden Markov model with a mixture of 4 Gaussian distributions. I have a total number of iterations of 533 times. Okay, the convergence, so I know that I have achieved convergence. I have my initial probability states represented for each of the 5 hidden states, and I have my transition matrix. And then there's also some other information related to the distribution parameters for each of these states and some statistical measurements such as the log likelihood and AIC and BIC. Well, now we will utilize the Viterbi algorithm to determine the hidden states of the data. So I'm going to launch the Viterbi algorithm here, and I'm going to predict the known values of the hidden Markov model. So if I'm thinking of this in terms of a data set that I'm looking at and how all of these concepts come together, I have a value of a particular row and the date on each row, and I know what the closed value is. But now, after running this approach, I can say, okay, well, what hidden state is it residing in? I know this isn't all that I can do, but this is just showing you how I'm working with hidden Markov models. So I actually, in this case, I bind them together using the cbind function, and I produce a data set very similar to what we have on the right-hand side. Well, once we have that, we can actually graph the results. Okay, we're going to create some scatter plots, and we're going to chart these series. And in the next couple of slides, we're going to see exactly how these data points relate to our time series. Okay, so let's begin. So the scatter plot produces the following line chart in QuantMod. Okay, so this is part of the QuantMod package. This is what we get out of it. And this is based upon the actual HWII stock data from 1/1/2013 to 2/17/2015. That's when I had run this data. Okay, and we can look at the line chart, and we can look at the shape of it, all the peaks and troughs, and the general trend. I mean, it seems to be fairly random in nature when we look at it. Okay, but there's some general trending in the components that occur with regularity. Well, now we will overlay the hidden states on top of the line chart to see the hidden Markov model represented graphically. So the first one I'm going to do is I'm going to plot all of my hidden states from the first hidden state. Okay, and we can see these as the little diamond points here. And I find this interesting, just what's the general shape of these points and the overall pattern, and is there something that I can detect, just visually from this? Then on top of the first state, we're going to bring in the second state. Okay, we now see these as like a magenta triangle as well. And I can continue going between the third, the fourth, and the fifth. And what we'll do is we'll just go ahead and we'll look at the final result. So here is what our final result looks like. And to me, we can see that all the data points are covered. Our hidden Markov model can represent all of the data points graphically here, and using the Viterbi algorithm, we see that it can account for it fairly well. So now that we've done this, let's create a prediction of tomorrow's stock price based upon the information that we've learned through the Baum-Welch EM algorithm and the Viterbi algorithm. So we're going to use these in combination with each other to create predictions. So here's some R code that will help us with these predictions. Unfortunately, it's not very cleanly wrapped in the RHMM package. Okay, so we're going to have to actually calculate these out, and you're going to have to develop some loops and functions to walk through the code. But in the simplest sense, this is the code that we need to use to create it. Once I've created, what the change is for a given day, okay, I'm going to take the most current date, okay, which we see at the bottom. I'm going to take the opening amount, and then I'm going to add what the change is as determined from our hidden Markov model. And then once we have this information, then I'm just going to add it on top, and we'll go ahead and open it up. So we see that for today's date, the open is 9500.04. Okay. Then walking through our hidden Markov model and drawing from the knowledge that we've gained, we now see that tomorrow's one we're predicting to be 9504.05. So this is giving an example of how we can use hidden Markov models for stock market data for prediction and decoding type purposes. All right, I'd like to thank everyone for joining today. This is a fun topic to get into. Hidden Markov models are really fascinating creatures and definitely an important tool in our toolkit. If you like this presentation, or if you have any questions on it, feel free to reach out to me directly or through the YouTube channel. And thank you for joining.